All right, let's get started. Welcome back. What were we talking about again? Concrete? Something like that? Few reinforced concrete. A few quick announcements. So the attendance grades are up to date, obviously other than today. Homework 1, was the grades were posted. Homework 2, don't forget that's due on Wednesday, February 7th. We've already covered everything in lecture for you all to be able to attack that homework assignment, so there's no reason that you all can't be grunting that one out. Does anybody have any quick questions on that one before we get started in lecture? It's one of those like, that was due Wednesday, February 7th, Dr. Mike. You really think we worked on that? You obviously don't know things. I know things. All right. So today what we're going to do is this. Let me sort of pull the slides back up from before we left. This was sort of the last thing that we discussed before we had our little break, and that was the concept of a Whitney stress block, the idea that if you're trying to ascertain the maximum capacity or maximum flexural capacity, that is, of a beam, we take that nonlinear stress distribution and we idealize it as that rectangular stress block. Now there were a couple things about that we sort of played fast and loose. Like, for instance, there is a difference between where the neutral axis of the beam lies, which is that distance C. There's a difference between that and how deep the stress block is, the difference between A and C. We really didn't talk about that because we really didn't need to for the purposes of assessing just MN. It's nominal moment capacity. So what we did is this. We did this example, and then what I want to do is I want to go back. I want to talk a little bit about some of these terms like beta 1, what are the ACI limits and things we need to assess. And then I want to go back to this problem and sort of revisit it. So just to recap everybody's, get everybody's memories jogged and whatnot. So this is the problem that we looked at before we left. So here was our beam. It was it's 10 inches wide, has an effective depth of 23 inches, 4 KSI concrete, 60 KSI steel. We took that nonlinear stress distribution and idealized it as the following stress block. So here we've got our calculation that we used to assess how deep that stress block was. And if you remember, we basically determined the depth of that stress block based off equilibrium, the idea that all the compression in the beam has to equal all the tension in the beam, otherwise the beam is running away from us. So we grunt that out. We found that the stress block had a depth of about 4.165 inches. Calculated nominal moment, and the nominal moment, give me one second, nominal moment was really just force times distance, just force times moment arm. The force didn't matter. It was C or T. We used T because I'm lazy, and that's 2 numbers to multiply instead of 4. And the moment arm's just D minus A over 2. So plug and chug, and you got 247 foot kips. Sound good? Take it away.
Now, when you calculate your 0.85 multiplied by FC prime, is that multiplied by the area of the block over there? So, like, if it's a triangle, would it be the 1/2 times the base times the height?
So you're asking about the homework. The answer to that is the answer to that is it's 0.85 FC prime times the area of that block that's in compression. So for a rectangular beam, it's B wide and it's A deep, okay? So for a triangular beam, it will be 1/2 base times height. Now the height, I'll go ahead and tell you, is going to be A, however tall the rectangle is. But what is the width? That was the hint, and we called it what, X? Figure out what X is. And I think you'll find it's not that hard. You just look at the dimensions of the beam. I think you'll say, oh, here's what X is. So, but I'm playing that one sort of close to the chest a little bit. Sound good? Anybody questions on this? Okay, so what I want to do is I want to sort of take a step back. I want to talk a little bit about some specific ACI provisions. I do this on purpose. I don't like to just throw it all at you all at once. I like to compute the capacity, then take a little bit of time, talk about the ACI provisions, and then come back to it. So let's look at ACI requirements for beams. And what we're talking about are limits on strains, limits on reinforcement, I want to talk about resistance factors, and what have you. So we'll take this one step at a time. So let's sort of keep this simple, okay? So let's start off with basics, okay? One of the first basic assessments that we are going to assume is we're going to make an assumption regarding the deformed shape of a beam. And one of those assumptions is that strains vary linearly from the neutral axis. Now, that's different than stresses, okay? We fully understand that the stresses are nonlinear. But one of the things we are assuming is that the stresses may be nonlinear, but the strains aren't. In other words, the beam, while the stresses are different, the beam deforms linearly. And if that's a little bit of a hard concept to understand, the easiest way to explain that, and the easiest way to kind of see it, if you take something like a notebook or something that has sort of a flexible book with a bunch of papers in it, if you take this, and watch this, if you take this and sort of just like draw a line along the pages, and then you take that book and you sort of deform it, like you bend it like that, you look, the line is rotated, but it's still a straight line. It's still a straight line. From the centroid, the deformation is still linear, okay? And so that's a very reasonable assumption to make for a reinforced concrete beam. So even if you have nonlinear stresses, we still assume that we have a centroid or a neutral axis that has zero deformation, and then above that we have deformation in compression, and below that we have deformation in tension. Does that make sense? So if you understand that, there's a couple things that you need to understand in order to fully define the strain profile for a beam. Okay? So let's talk about strains. One of the ACI assumptions that we always make for a reinforced concrete beam, and this is true regardless of compressive strength, is that the maximum usable compressive strain that a concrete will experience, we take that actually to be a constant value of 0.003. And the idea is that regardless of if you're looking at 3 KSI concrete, 4 KSI concrete, 6 KSI, what have you, regardless of the strength of the concrete, the maximum usable strain, to keep things simple, we pretty much take that to be a value of 0.003, and we just treat that as a constant. Now, I guess we could be a little more accurate. We could say, well, maybe we could develop a model or an equation that better calculates that for different for different grades of concrete. Bless you, for different mix designs. The problem with that is there's something to be said about taking concrete design and making it too complicated. You want to keep it straightforward, and you want to keep it applicable. You also have to look at the ramifications. Ultimately, what we're doing here is we're making a conservative assumption about the behavior of the concrete, because really what we're going to do is we're going to use this assumption just to make sure that the steel yields. So it actually makes a little sense to be on the conservative end. So one of the things that we're going to do is automatically assume that the maximum strain in our concrete is 0.003. So if I'm looking at this, so here I've got a reinforced concrete beam. Now over here on the right, I've got the stress profile, and this should be familiar. You know, our stress block is 0.85 FC prime in depth, or in width, if you will, and it's A tall. That's the stress profile. The strain profile, how it deforms, is what we see here in the middle, in this sort of blue component here. So what we're saying is that the neutral axis has zero deformation. Above that, we have linear deformation in compression. Below that, linear deformation in tension. So when we're generating our strain profile, one of the things that we know is this value right here. The maximum strain on the top is 0.003. So think about it like this. The idea is if I know that this is 0.003 and I can figure out this depth C, you can basically just use similar triangles and say, well, if I know this value and I know this depth, and I can figure out this depth, I can determine what this strain is. So basically what we're doing is we're saying, well, I can use the strain in the concrete to figure out what's the resulting strain in the steel. And the reason why that's important is because we want to ensure that the steel yields, okay? We made an assumption when we did our analysis last time. We assumed that the tensile force in the steel was ASFY. In other words, we assumed that it yielded. We have to verify that assumption. And that's where this comes into play. But don't worry, we're going to do the math on this here in a little bit. Now, one of the other things I want to talk about is, well, how do you determine where the neutral axis is? Remember, I want to be clear, there is a difference between how deep this stress block is and how far it is from the top of the beam to the neutral axis. There is a difference. The depth of the stress block is referred to as A. The neutral axis, the top to the neutral axis, is referred to as C. Okay? Now, while we do assume a uniform compressive strain for steel, one of the things we don't assume is a uniform relationship between these two values. The difference between A and this term C is an empirical value called beta 1. Now, beta 1 does change with the type of concrete, okay? So for instance, the idea is, here's sort of the general idea. If you have a concrete that is very, very strong, we're talking 7 KSI, 8 KSI concrete, etc., it can reach a lot of strength, but one thing it does have a little bit of an issue with is ductility. It's not as ductile. So your stress strain curve tends to be way more pronounced. And that would ultimately change what your stress block would look like. So the idea is that as your compressive strength goes up, your beta 1 value actually goes down. And it's pretty much what we use in the code is we basically say anything less than 4,000, your beta 1 value is 0.85. Anything greater than 8,000, your beta 1 is 0.65. And in between, it's a linear relationship. So for instance, if you were using, I don't know, 4,500 PSI, well, it'd be between these two, so something like what, 0.825? Does that make sense? Everybody okay with that? Now, I want to be very crystal clear on this, okay? This last example that we just did, this was 4,000 PSI, right? So I have here that beta 1 is 0.85, okay? Now I got that from this chart here, that for 4,000 PSI concrete, beta 1 is 0.85. But a very natural question I always get is, okay, this is 0.85, you know, what about this? Does this change? The answer is no, okay? I don't care what concrete you're dealing with, this is always 0.85, this beta 1 is what changes. So if you were using, you know, 8 KSI concrete, this would be 0.85, this would be 0.65. That always changes. The beta 1 always changes, but the 0.85 on the top remains the same. And again, you got to remember, we're talking about empirical relationships that are used to simplify really complicated behavior. So sometimes some of the terms and the provisions can be a little wonky. It's sort of something you just kind of have to get used to in upper level engineering practices. So far, so good? Okay. All right, a couple other things. Okay, ACI also has a limit on the amount of reinforcement that you can put in a beam. Like, you can do the math, and the math could state that you only need like half a square inch of steel. But you calculate, you go about this limit, and the limit says, I tell you what, I know that you did your design, and the design said you only need half a square inch of steel, but this ACI limit says you need 2 square inches of steel. Well, you're putting in 2 square inches of steel in order to satisfy the ACI minimum. Basically, the idea is that this is ACI's way of guarding against sudden failure, okay? The idea is, you know, you're doing your design, you want to at least meet this limit just to guard against sudden failure events. Now, to be perfectly honest, in most of our design efforts that we engage in throughout the semester, this isn't going to be a big deal. We're going to check it, and then we're going to find that we're on the other side. Like, we'll get 0.8 square inches of steel for this, but we put in like 3 or 4 times that, so it's not a big deal. But it's just something that, to be aware of. Now, a couple things on terminology. We know what D is. We know what Fy is. Remember, a square root of Fc prime, you put in PSI, you get out PSI. The B sub W is the width of the web, but if you have a rectangular beam, that's just a B. Those terms that you're seeing, if they're new, we'll be sort of using those here in a little bit as the semester progresses, so don't worry too much about that. Okay, excuse me. So here's my strain profile. If you can figure out what C is, and you know the strain in the concrete at the top, we can figure out what the strain is right here. This is the strain where the steel is. And you'll see why that's important here in a second. But, oh, sorry. So here's the here's the way we do that, and it's basically just similar triangles. You know, this is to this as this is to this. So 0.003, this quantity is to C as whatever this quantity is to D minus C. It's basically just slope ratios. It's a lot like what we did in almost something like this, similar in structural analysis or something. Really just slope ratios. So we're ultimately after this quantity here, so take this, multiply it over, so 0.003 times the quantity D minus C over C. Does that make sense? So that will tell us what the strain in the steel is, okay? The reason, well, yes?
Is that line showing us the stress?
No, this is the strain. The strain, yes. So the values are going to be a lot smaller. They're not going to be like 20 KSI or 30 KSI. They're going to be like 0.004, 0.005. They're going to be really small. And you'll see, I'll be able to elaborate on that here in a second. Sound good? Okay. Here's how we determine whether or not the steel has yielded. All right, so here, oh, don't tell me. You got to be kidding me. The pen's not going to work. Woo, I'm not going to be happy about that. All right. Hold on. Okay. So let's say we've got our stress strain curve, right, for steel. You make do. You make do. All right. Oh, wait, I got a marker. So sorry, YouTube. Okay, so here's my strain, here's my stress, okay? So if we're just talking about zoomed into the linear range, if you recall, steel kind of has a behavior that's linear, and then it yields. Now, granted, you know, all the way out here, it'll start to go out, and you'll have that strain hardening effect, but we're not really dealing with strains in the bending region that are that high. So really what we do from an analysis standpoint is we say it's either elastic or it's not. It's either elastic or it's experienced yielding. So this slope, that's E, that's Young's modulus. What's the E for steel? There we go, 29,000 KSI. Okay, so this maximum stress right here, that's whatever Fy is, right? So what I can do is I can then say, all right, let's take that. Let's figure out what that is, the strain at yielding. So pretty straightforward, just take Fy and divide it by E. So if I've got, let's say, 60 KSI, then 60 KSI grade steel, then the Young's modulus for steel comes out to be around if the Young's modulus is 29,000, then the strain at yielding comes out to be around 0.002. Make sense? So what we would then do is take that strain and we would compare it against what we're actually getting in the beam. And what we hope to see, for instance, if the steel will yield at like 0.002, we actually kind of hope that we see like 0.006 or 0.007. And that might seem kind of weird. You're like, what are you talking about, Dr. Mike? You actually hope that the steel yields? Actually, yes, I really want the steel to yield. And I'm going to explain why. Okay? A couple reasons. Well, it's not really a couple reasons. Let me just sort of lay out there on the line. Okay. So I just said a second ago, I really hope that the steel yields. I want it to yield. Okay? And that might seem a little weird, but here's why. Okay? I have two components in a reinforced concrete beam. I have the steel and I have the concrete. Okay? Now if I bend a reinforced concrete beam, I got concrete components in compression and I got steel components in tension. Make sense? So I obviously don't want failure to occur. I'm a structural engineer. I want everything to be fine. But if I'm trying to determine maximum capacity, I got to look at it realistically. And if I take this beam and I load it, the facts are one of those is going to fail first. It's either going to be the concrete in compression or it's going to be the steel in tension. It's physics. One's going to happen first. What I hope that the steel fails first. I want the steel to yield before I want the concrete to fail in compression. The reason why is this, okay? For those of you that had civil engineering materials with me last semester, you know that if you take a concrete cylinder and you load it in compression, like once it's gone, like it's done. You know, and some of the failures can get quite sudden. You know, you have a concrete cylinder that's been dried out for a while. It's been, you know, let's say we're talking about a beam that's been in service for 10 years or something, and it experiences a load. When that concrete fails in compression, when it goes quick. Boom, right? Okay, that's how concrete fails in compression. Now, what happens when steel yields? It just gets a little longer. Like, so what, right? I'm not saying it's desirable. I'm just saying that if we're being honest, steel experiencing a little bit of yielding is a whole lot better than a concrete element experiencing crushing strains. Like, it's going to go. This is serious, okay? So some of the limits that you're going to see here in a second reflect that, okay? So, for instance, according to ACI, one of the limits that is set forth right off the bat is that the strain in tensile steel is limited to 0.004, okay? Now remember, grade 60 steel, it yields at 0.002. So right off the bat, this is the limit that ensures that the steel yields, okay? So all tensile reinforcement in a beam has to yield. That's what this limit is basically saying. Now this limit is set forth for basically any member anywhere. But it also says in the code, it says, this is members with axial loads less than 10% of FC prime AG. So what type of members are going to have axial loads greater than at 0.10 FC prime AG? Just curious, what are we talking about here? We're talking about beams right now. What limit would this not be appropriate for? Columns, because columns aren't experiencing any tension. They're just pure compression. So this wouldn't even make sense to apply for a column because there's no tension at all. So it's something you got to be aware of. Sometimes a lot of these limits are generalized, but then they'll have language like this. What they're basically saying is we're not talking about columns here. So this is a limit purely for flexural elements that's experiencing compression and tension. Okay. So far, so good? Okay. So first thing I want you to keep in mind is that for beams, the strain always has to be 0.004 or higher. Okay. What the code does is it goes a little bit further and it actually classifies some behavior in some very specific terminology. What it does is it basically throws two terms out at you. It throws out either the term tension controlled or the term compression controlled. Okay, so in its simplest terms, a member that is tension controlled is basically controlled by the failure or the behavior of the steel. A member that is compression controlled is controlled by the behavior of the concrete. Okay? If I'm designing a beam, it would be more desirable for that beam to be tension controlled because, again, if the steel fails first, then the steel just gets a little longer. It just yields, and it's okay. If the concrete fails first, we got problems. Make sense? Everybody okay with that? So if I have a reinforced concrete beam and I load it and that beam is tension controlled, what's going to happen is I start to load that beam and the first thing that fails is the steel. The steel starts to yield. So what you would start to see is you would start to see very, very large deflections. Like you would see the beam sagging. You would see a lot of stuff going on. So there would be a very significant warning to a user before failure. I mean, if you see a beam like this, move, you know. Get out of the way. Okay, that's a tension-controlled element. A compression-controlled element is on the other side. A compression-controlled element is governed by the behavior of the concrete as opposed to the steel. This is really what we don't want to have happen. This is where the concrete crushes before the steel experiences yielding. So if you were to take a compression-controlled element down to the lab and load it, what would happen is it would be very akin to the flexural tests that we did in 321. Yeah. Boom, gone. Okay? So there would be no ability to walk into the room and see the beam sagging and get out of the way. You'd just be there and, well, that's it for you. But in all seriousness, the deflections would be very small. They would be very imperceptible, and you'd have very little warning of failure. So we have to make sure there's a difference in our understanding of what's a tension-controlled region and a compression, or a tension-controlled section and a compression-controlled section. We also have a third term that we call transition. That's sort of somewhere in between, and I think that'll be clear here in a second. Now, the way that the code handles the use or the classification of a tension-controlled section or a compression-controlled section is through the use of a strength reduction factor. Okay, you all remember on homework 1 how we were taking dead loads and live loads, and we were bumping them up, right? We were taking the dead loads and we're bumping them up by 1.2, taking the live loads and bumping them up by 1.6. Okay? The reason that we did that is because we were less certain, we had more uncertainty associated with the live loads than we did the dead loads, so we took the live loads and we bumped them up more, right? The idea was to get a uniform level of safety, but all that was on the load side. Now what we got to talk about is uncertainty and behavior on the resistance side, on the strength of the concrete beam. Okay? And the way that we handle that is we take that nominal moment capacity, that Mn that we computed in that previous example, we take that and we adjust it by a strength reduction factor. We call that value phi. Okay? Now, what's interesting about concrete design is that phi changes depending upon the behavior of the beam. See, phi is actually a lot more complicated in here than it is in steel design. In steel design, because you're primarily dealing with elements that are of a single material, it's just, oh, columns, phi is 0.9. Like, you just look it up. There's no determination. But in here, you actually have to determine that. Now, I want to take this chart, and I really want to sort of dig into it a little bit. So what we're seeing here on the x-axis is the strain in the steel. So as I go to the right, the strain in the steel is getting higher and higher and higher. And on the y-axis, I've got my strength reduction factor. Now, let's look over here on the very, very right. Okay, on the very right. Tension-controlled regions. So we're talking about regions where we've got a lot of strain in the steel, right? So remember, where does steel yield? About 0.002 for grade 60? So we're talking about 0.005 and higher. So really, really high strains in the steel, okay? I propose that, well, I don't propose it, ACI proposes it, but ACI states that they define a tension-controlled section as any section that has really, really high strains, specifically strains that are higher than 0.005. And anything past that, we take our resistance factor to be 0.9. Because remember, there are still uncertainties associated with the construction process, and et cetera, et cetera. So we do still reduce our capacity, but we reduce it by 90%. So we would take that phi, if we had a tension-controlled region, or a tension-controlled beam, we take its capacity and we multiply it by 0.9, okay? Now, let's take a look at the flip side. Let's take a look at a compression-controlled section. A compression-controlled section is one where the tensile strains are less than yield. That's compression-controlled. That's concrete fails before the steel does. That's bad. So what is our phi value? It's 0.65. Think about what we're doing here. We're saying, okay, now we've got a beam that's compression controlled, and if it fails bad. It fails dangerously. So we're going to take its capacity and we're going to reduce it further. Instead of multiplying by 0.9, we're going to multiply by 0.65. So the amount of usable capacity becomes less and less to us as engineers. So what it ultimately means is if you got a compression controlled section, it'd have to be a lot bigger. Does that make sense? Everybody okay with that? So that's tension controlled and compression controlled. This is a transition region anytime your strains are between the yield and 0.005, and in order to do that, you just take phi and you calculate it. It's a line. It's just y equals mx plus b. So here's your line. You can calculate the slope. There's your equation for that line. The only thing that you don't know is epsilon sub y, your yield strain, and that's just calculated right here. Does that make sense? Okay. Any questions so far? Now this slide here, this is getting really nitpicky, and to be honest, we probably won't deal with this at all during our semester. I just wanted you to have this for your own edification. So there is a difference in notation between the strain at the bottom layer of the steel and the strain at the centroid of where the steel is. And what I'm really talking about are beams that have 2 layers of reinforcement. Honestly, we're really not going to deal with this very much in here because most of the beams that we design, we're just going to design a single layer of reinforcement. But I just want you to be aware that in those slides, if you ever saw any sort of discrepancy or difference between epsilon sub s and epsilon sub t, epsilon sub s is at the center, epsilon sub t is at the very, very bottom. But again, those are mostly going to be the same for everything that we do in this semester because we're only going to be talking about a single layer. Does that sound good? Any questions so far? All right. Let's take a look at this. So what I want to do, I want to take the example that we literally just did, and I want to take it and evaluate ACI requirements, ultimately determine its phi value, and et cetera. Now let me see something real quick. Hold on, I'm going to pause this real quick. So for you YouTube folks, we've determined that the marker isn't going to work. I'll post a summarized solution later so that the playlist is complete. But yeah, just check out the next video.